Okay, let's talk about one of the most important imaging techniques to emerge in the last couple of decades, and that's magnetic resonance imaging. The big appeal of magnetic resonance imaging is severalfold. One big one is that it uses non-ionizing radiation. It uses radio waves to construct its images. These radio waves have such a low energy state that the risk to participants is extremely minor. Therefore we can do multiple scans, we can scan many people, we can do repetitive scanning without the fear of the potential health problems that we see with things like ionizing radiation. The technology has also dramatically improved with time, allowing for some impressive resolutions. And probably the most important development lies in the functional magnetic resonance imaging, which we'll talk about in the next video. But let's just talk about the MRI machine itself. So MRI imaging became popular as a whole body imaging technique. You can see that there's this large bore, this hole, and inside that you're basically moving the person's body into a gigantic magnet. Modern MRIs that have been constructed specifically for research no longer focus on just the whole body, but rather on just the head, allowing for even stronger magnetic fields. And we are talking about very large magnetic fields, several orders of magnitude larger than the Earth's magnetic field. These are gigantic, powerful magnets. So, why? Why are we sticking people in giant magnets? I think a good place to start is to think a little bit about a compass. So a compass is going to point north towards the magnetic field of the Earth, right? But we could, for example, take a stick and apply it to the compass needle, and we could flip that needle around so that's now pointing south. As long as I'm holding that needle, it will continue to point south, right? This is what we call a high energy state. It's unstable, right? It doesn't want to stay there. As soon as I remove my finger, the needle is going to flip around right back to north, right? And when the needle is oriented towards north, that's the low energy state. It's stable, right? So this is really important because this is the basic way in which the MRI functions. We place the person inside the MRI, and all of their water molecules, which produce a tiny magnetic field, align with a giant field underneath, surrounding the body. So how do we actually create an image? Well, what we're actually taking a picture of is the magnetic properties of the tissue that surround it. For example, let's go back to this compass model. And instead, say I got 3 compasses flipped over upside down so that you can't see what's in them. One of them is filled with water. One of them is filled with a thick syrup. And the other is just air. If I take my finger and I flip these compasses around so they're all pointed south, what's going to happen when I lift my finger? So think about what's going to happen in the syrup, the water, or the air. So I'd actually ask you to pause the video for a minute and to think if there would be a way to determine what is inside each of the compasses just by looking at what happens when I release my finger. Okay. So if we're sitting here looking at this, right, what we should see is that if this compass, for example, contains air, as soon as I lift my finger, it should go right back to north very, very quickly. If this compass contains water, it'll be a little slower. And the amount of time it takes the air compass to go north, it might only go halfway. In the thick syrup, it might only move a little bit, right? And we can actually take an image at any point in time and see where the needle is. And that'll actually tell us the thickness, the viscosity of the liquid inside the compass. And this is exactly what we're doing with the MRI. As we put somebody in the MRI, we magnetize the water molecules, then we energize them. We hit them with those radio frequency waves. We're talking about the non-ionizing radio frequency waves that energizes them so that they're aligned in the opposite direction. And then we turn the energy off and we wait half a second, and then we take a picture. And we see where the water molecule is pointed, how much energy is left in it, and we construct a grayscale image from white to black, depending on how much energy is in there. And it turns out different kinds of tissues are going to produce different kinds of structures, different kinds of colors. We can actually virtually slice the body up as well. We can create slight differences in the magnetic field along the axis of the body, which means that we can resonate those water molecules only within a given slice. And this lets us actually cut the body into slices. And we talked about the various directions of the slices, at least in terms of neuroanatomy, right? The sagittal, the horizontal, and the coronal slices. So when all is said and done, we're left with the image of the person. Right? And we can see very concrete structures here of the person's face. And because of the slicing mechanism, we can actually cut in and see what the brain looks like. So this here is a typical 3 Tesla. Tesla is a strength of the magnetic field picture of the brain. And hopefully you can tell that we have actually a lot more structure and resolution than in either the CT scan or the PET scan. Right? This is the typical research strength MRIs that are out there now, but there are some ultra high field MRIs out there that are taking even more impressive images. So here is some examples of ultra high imaging, and hopefully you can see the innate detail that we are able to pick up, the structures of the brain, just some incredible resolution. This is an angiogram. I remember we talked about those with x-rays, where we can see the actual vein and arterial structures of the blood flow of the brain. Just some incredible images that are coming out of MRI. So again, the main strengths here are that they're non-ionizing, right? So there's not nearly the risk to the subjects as an ionizing radiation. And they have some amazing resolution capabilities. But the big deal, though, came with the discovery of the blood oxygen level dependent signal, or the BOLD signal, and that is the fMRI, which we'll talk about in the next video.